Concave up, concave down. Question. Even though we haven't taken notes on it, even though you haven't written any forevers on it, question. How have I already alluded that we can figure out about concavity? What can we use? Slopes tell me, first derivative, increasing, decreasing of the original, whether slope is positive or negative. How the slopes are changing, slopes increasing or decreasing, can tell me about the second derivative. And that translates in, do you guys remember from yesterday, our little example? We were talking about the second derivative a little bit. Question, the second derivative was always positive. What concavity did he have? The second derivative was negative everywhere over here. What concavity did he have? Everywhere negative infinity to 0. Oh, negative second derivative concave down. 0 to infinity, I had positive second derivatives and he was concave. Do you see a correlation? Positive f double prime, concave up. Negative f double prime, concave down. Positive f double prime, concave up. F double prime 0, maybe an inflection point, come back. So if I needed my f prime for my increasing, decreasing, I'm going to need my f double prime for my concave up, concave down. So guys, what is my f double prime for this function? 6x. I'm going to zoom back in because it's going to get ridiculously small. Here we go. If f double prime of x is equal to 6x. And if I want to figure out the signs of f double prime, Jazzy, what are you talking about, kiddo? Can I answer any questions for you? Okay, then let's focus back this way. Signs of f double prime can also tell me about the behavior of f. But just like we did with f prime, guys, how did I mark the key numbers in the sign chart again? I found the derivatives zeros. That's going to be the same for concavity. I'm going to find the derivative zeros, which are going to be at x equals. Oh, he's my only one. He's the only place where the signs of f double prime can change. How am I going to figure out the signs of f double prime on this interval? I could graph them or I could just plug it in. So when I plug it in, what's f double prime of test point?
Negative 10.
Negative 1, negative 10, negative 100, I don't care. They'll all be the same. Plug it in and you have a negative. How is that going to translate to the graphing behavior of f? Negative second derivative means the slopes are decreasing, aka I am concave down, like a frown. If I go to my next interval, I could plug in, be creative this time, guys. 32, thanks, Nick. Doesn't matter, right? It doesn't matter. I just don't want some of you guys to be like, how do you come up with the magical number? Pick one. 32, plug in. Nick, what do I have? Positive. And if he's positive, that means that, what's my behavior of f going to be doing? Smiley face, there you go. So, for my, come on back. Remember, I'm trying to show you one worked out A, B, C, D, E. What would my C be if it's where, guys, let's make it easier on ourselves, where it's concave up? What's my interval? Negative infinity to? Concave. I'm just writing what you guys are saying. Concave up at?
0 to 100.
Concave down at? Uh-oh. What was part E? Does anybody remember?
Inflection.
Inflection point. An inflection point A has to be a point. Wait, seriously? No, seriously. Seriously. First of all, to be an inflection point, first it has to be a... No. To be an inflection point, first it has to be a point. So it can't not exist? It can't be a hole? It can't be a vertical asymptote? It can't be a break in the graph? Double checking. To be an inflection point, first it has to be a point. Okay. Then what else has to be true? It has to be a point at which the graph changes concavity. Question, at x equals 0, A, is there a point at x equals 0? What am I looking at? Can I plug in and it exists? Okay, so first he's a point. And question, is he a point at which concavity changes? So therefore, my inflection point is at 0. Oh, man. 0 what?
Negative.
0 minus 0 is done. Okay, that's A, B, C, D, E for an example. How did I know it was an inflection point? Because I looked at my sign chart for my second derivative and said, look, he changes at, got it. He has to be a point, he has to work, and the concavity has to change to be an inflection point. Emily.
I'm a little confused on if we're doing F double prime, like it's primary track double prime, why are we putting it at the original function?
We're using F double prime signs to tell me about the behavior of the original function, but I'm also looking for the concavity, the increasing, decreasing, the inflection point of the original as I uncover my clues about my derivatives. I'm still like just trying to unearth what's going on to that function. So I'm figuring out things like f prime is positive or negative or positive, f double prime is negative or positive, but I'm always bringing it back to what's f doing? What's f doing? What inflection point, what is the inflection point of f? And so if you look at your graph, which I cheated a little bit, I graphed him. Is it concave down from negative infinity to 0? Is it concave up from 0 to infinity? Is it increasing, decreasing, increasing? I'm thinking about him, so when I'm thinking about concavity changing, I'm thinking about his inflection point. So given an x, I need to find his y.
And so all of the answers, like before boxes like A, B, C, and D are all of the original.
Got it. As demonstrated by what we saw in the derivatives. With that, guys, here we go. We are going to start today. We're going to have to finish tomorrow. If you want to look at, these are all going to walk us through the steps for how to approach any problem having to do with concavity, having to do with increasing, decreasing. There are some important forevers along the way. Let's start here. Technically, this should be all review. I'm going to make them all green. Strictly monotonic, we have talked about a lot, especially when we are trying to think about the invertibility of a function, whether a function was 1-to-1 or not. Why am I talking about him here? Well, we're talking about increasing and decreasing here, right? First of all, we're talking about increasing, decreasing here, and second of all, if a function is strictly monotonic, aka if his derivative can only be positive or only be negative, what's the point of a sign chart? I mean, we can make one. But if he's a function that's only positive or only negative, well, it's only increasing or it's only decreasing, I guess he could make a sign chart, or he could just say he's strictly monotonic. But most functions aren't. Jess, you have a question? So that's just quick review. Since we're in the increasing, decreasing section, how can we not review strictly monotonic? But then we get to a definition. Now the good news is for us, the new pre-cal book last year already had us use sign charts. Not for quite as cool things as you'll be doing this year, but had us use sign charts and also had us find key numbers. Now I might have slipped up, maybe on purpose, maybe accidentally last year and called them critical numbers a couple times. Key numbers last year are critical numbers this year, except critical numbers are specifically talking about a function's derivatives, 0 or non-existent points. So critical numbers, I'm not talking about like nonlinear inequalities from last year. I know you guys probably don't remember, but I just taught it to Honors Pre-Cal a little bit ago. Nonlinear inequalities, you had to take whatever was there with like a greater than denominator is equal to 0, put them all on a number line or in a table, and test each of the intervals and say, does he work, does he not? Well, we're not taking all the zeros and undefines of the original. We're taking all the zeros and undefines of the derivative to find critical numbers. Guys, what's so special about the zeros of the derivative? Horizontal. Horizontal tangent line, right? What's so special about the DNEs of derivatives? Vertical. Or, isn't there another way that I could have a non-existent derivative? Continuous but not differentiable. I could have holes or vertical asymptotes, which would be a whole other problem. Or vertical tangent lines or sharp points. There was that forever card. Let me zoom in a little bit. We should be past strictly monotonic, I hope. Now, quick reminder, I think I've shown you this before this year. To find the critical numbers, if f prime of x is a rational function, what's it mean to be rational? There's different ways you can think about, like numbers that are rational are ones that can be rewritten as a fraction. Rational functions are ones with an f of x over g of x or a p of x over q of x or however you want to say it. If f prime of x is a rational function, define my horizontal tangents as at the top, the numerator equal to 0. To find my vertical tangents, that's when my slope does not exist, which would be setting the bottom equal to 0. Let's write this differently. That looks weird. Set the bottom equal to 0, which would be a non-existent derivative, which would be like a vertical tangent line. Guys, I'm not writing sharp points down because you won't I can't even talk. You won't see sharp points in a rational function like solving for zeros. You're going to see sharp points because it's going to come from a piecewise function, a piecewise derivative that doesn't match up, that's not continuous. A piecewise derivative that's not continuous. The separators, if you plug in, it doesn't match. That would be a sharp point. Now, Jezreel, you said something like the derivative won't exist at a hole. What do you mean by that? I like it. Why wouldn't the derivative exist at a hole? There's nothing there. So if there's nothing there, can I have a slope at nothing? A slope of nothing? No, I can have a slope before or after, but I can't have a slope of nothing. So technically, we have to watch out with this hole where the derivative does not exist, because the derivative might not exist at a discontinuity of the original, like a vertical asymptote or a hole. If there's a vertical asymptote or hole, can I start saying that there's like increasing, decreasing, inflecting going on there? No. So we're going to write a watch out in just 1 second. First of all, make this forever number 17. It's kind of like key numbers from last year. We've solved for the zeros of the top, zeros of the bottom to put in for our sign charts. This is for a much different purpose. Let's talk real quick about those watch-outs that Jezreel just said, like, oh, well, the derivative won't exist at a hole. Okay, she's right. Careful. The derivative will not exist when the function does not exist. Hopefully. If it does exist, I'm in trouble. So I have to watch out for, hold on, this is review. Holes were removable, right? How do you know it's a hole? Set denominator equal to 0, plug in, and it's, keep going, right? Vertical asymptote, what was that one? Yeah, non-removable. Set the denominator equal to 0, plug in, especially if it's like a nasty function, if I get a number over 0. Jumps, well, they're going to be funny piecewises that don't connect. I can't talk. Well, you can say pieces don't connect. You guys get that, right? Pieces, if it's defined in pieces, it has to be a piecewise. Don't connect in a separator. All of this is talking about domain problems of my original. Let's actually write original. It's not always named F. Gotta watch out for domain problems of the original. And I'll keep reminding you of this note, but I want it in there in this section where we first start talking about analyzing graphs, analyzing functions and their behaviors. That leads us into, all right. Does anybody remember what we're doing now? We were like doing derivatives for forever, and now we're like talking about concepts. What are we leading into? Applications of derivatives. And we're starting here with analysis, but what do you think I'm trying to lead you into? Word problems that can only be answered by analyzing derivatives. How many different word problem types, scenarios do you think AP guys can come up with? Lots. Everything from shoveling snow to processing gravel in a plant to having chemicals drain out of a conical tank to, okay, it gets crazy. Somebody riding a bike to school, that was a bad one. They can come up with all kinds of things, guys. But the nice thing with AP Calc is that they still come back to certain keywords, and increasing and decreasing are two of them. Doesn't matter the scenario, doesn't matter the problem. Increasing and decreasing, whenever you see them, it's always going to be talking about a quantity is increasing, a quantity is decreasing. Either they give it to you or they're asking you to find it. And it always needs to point you to what is that quantity prime's sign. What is that quantity prime's sign? If I want to figure out about increasing or decreasing, what is that quantity prime sign? If I know the quantity prime, look at the sign, I can tell you what the quantity is doing, increasing or decreasing. And it might seem silly because you're like, well, that's super obvious. The slope is, so the function is, but I'm still going to make it a forever because these are two huge keywords. That was really awkward. For any AP Cal question. Forever number 18. So you might think it's silly that I'm boxing this right now. Like, why are you making that a forever card? Believe me, I know. This, increasing, decreasing, keywords. If I want to figure out where a quantity is increasing or decreasing, look at quantity prime, whatever it is. Might not be F, might be G, might be F prime. Where is F prime increasing or decreasing? Ooh, F prime's prime, F double prime. Anyway, this is what I started doing at the beginning of class yesterday, and I finished off today. This is not going to be a forever card. Oh. This is not going to be a forever card. However, it does for some of you guys who are like, great, you gave us an example, but what were you doing? This is what I was doing.
Wow.
And this, just a hint, will be the exact same thing, the exact same steps for concavity, except instead of solving for the first derivative, I'll be in step 2 solving for the second derivative. Instead of finding critical numbers of the first derivative, I'll be finding critical numbers of the second derivative. Instead of making a sign chart for the first derivative, I'll be making a sign chart for the second derivative. Instead of plugging test points into the first, okay, you guys get the point, right? So even though I'm splitting it up because they are two separate ideas, they are still definitely linked in how to solve. So yes, we are going to take time. I'm going to underline a few things just to simplify the process for some of us. And once again, you don't have to write every word. Some of you should. But I would still have a brief outline of the process. Step 1, find original function discontinuities, aka find the domain. It's because of my watch out. Things can change behaviors can change at discontinuities like vertical asymptotes or holes. Well, holes not so much. Vertical asymptotes, yes. So I have to consider discontinuities. Step number 2. I need to consider the derivative function and its critical numbers. Step 2, I have to consider the derivative function and its critical numbers, which is what we already talked about. Top equal to 0, horizontal tangent lines, bottom equal to 0, vertical tangent lines. Because either intermediate value theorem, either behaviors could change at zeros of the first derivative, or behaviors could change at discontinuities of the first derivative. Then I'll take everything I've collected from 1 and 2, any domain restrictions, any critical numbers, and I'm going to make a sign chart, which you've already seen me model for you. So 1, find discontinuities. 2, find critical numbers, first derivative. 3, sign chart. And I'm giving you step by step, literally. Some of you want this. Test those intervals. Figure out the signs of the derivative. Make a conclusion, increasing or decreasing about the original from that. And if you follow this procedure for any function, no matter how messy, you will be able to figure out on which intervals it's increasing or decreasing. However, there is one little note. When you solve for the derivative to find the critical numbers, A, not all functions are rational. What? Well, you could make them rational, put them over 1. If it's over 1, though, can 1 ever be 0? You don't always have to find the zeros at the top, zeros at the bottom, because there's not always a top or a bottom, or maybe it's not possible to have a 0 in the top or the bottom. That's one thing to be aware of. I still want to find the zeros, and if there's a denominator, find the zeros of the denominator as well. However, derivatives, guys, I did an easy one in my example. Can these derivatives get nasty? Oh, there was not a resounding yes on that. Can these derivatives get nasty? Yeah. And maybe what was one reason for me giving you multiple choice, maybe even what some people would say early on in your calculus course, to make you simplify, because if you don't simplify the derivative when it comes to doing the pitchfork, it's going to be a mess. And I wish I could pull out a board and show you one from this morning. Some of these can get to be a mess. And if you do not simplify into a common fraction with 1 numerator, 1 denominator to set equal to 0 for horizontal tangents, equal to 0 for vertical tangents, if you do not simplify, it's going to be a mess. And that kind of brings me to, hold on, pause, where are we? He's way too easy. Can somebody turn in your books real quick to number 18? Number 18, he's a homework problem, or maybe you have it on your paper. I'm going to show you real quick. I'm going to prove my point. Guys, these are going to be online. Actually, I'm going to save all the way through the end of section 5.1. You can copy it down today if you want and just be paying attention tomorrow. Number 18 in your homework is one of those A, B, C, D, E ones. What's my function for number 18? Anybody? Plus 2? Okay. When I start, and I'm just proving a point, that you can either start tonight by trying to do the whole shebang A, B, C, D, E of each of those, or just say, I'm doing increasing, decreasing, I'll wait on concavity, or saying, I'm just finding derivatives and simplifying, and I'll wait for the rest. Here. First step, domain. Just a hint, my domain is all real numbers. Some of you might see why it's all real numbers. numbers, some of you might need to set the bottom equal to 0 and see it. Second step would take me to f prime. Guys, when I get f prime, you know we have to use quotient rule, right? If I want to find my critical numbers, which is a very important step two of the process. Question, do I want to solve for equal to 0 right now before I've simplified or after? Well, you might be like, well, it's not that big a deal, is it? Okay, fine. Maybe it's not that big a deal in this one. So maybe we wouldn't do that yet. Maybe we would do it here. But question, maybe this one isn't that big of a deal to simplify yet, but what's coming when you get to concavity? What are you finding instead of the first derivative? And if you just took the first derivative, do you think the second derivative might be a little more involved? My hint tonight, if you don't want to do like split up your homework, increasing, decreasing now, concavity later, derivative first and second of all the problems 11 through whatever, simplify them to the best of your ability. I'll have answers to derivatives tomorrow. Without them, it's not going to work out well. Bye, guys. Tomorrow's concavity and examples.